There is another way that we can compare the acidity without knowing pKa values, and we call that qualitative approach. So you don't need to know the pKa values all the time. In this approach, we need to look at the conjugate base. So imagine if you have an acid like hydrochloric acid, if it gets deprotonated, loses the proton, it converts to the conjugate base. And we are going to look at the stability of this conjugate base. The more stable the conjugate base, meaning that it has the stronger acid. There are a few factors that can influence the stability of the conjugate base. They are atom, resonance, induction, and orbital. So there is an acronym for them. You can remember ARIO. It's easier to remember them. So we are going to look at these factors and see how they can influence the stability of the base, and how we can use them to determine which acid is basically stronger than the other one. The first factor is atom. We can compare the atoms in some cases. So if you look at the structure of butane and compare it to this alcohol, so as you can see here, the only difference between these two is that I replaced the carbon here with oxygen. Now, to determine which molecule is more acidic, we need to use ARIO here. And to use that, we first need to draw the conjugate base of each. To draw the conjugate base, we need to remove the proton from each compound. So for this one, I remove the proton. This is the symbol that shows that I am removing the proton, and that gives me this anion. Now in the second one, if I do same thing, this is gonna be my anion. So remember that divalent oxygen already has 2 lone pairs on it. So if you compare these two anions, in the first one, I have the negative charge on carbon, and in the second one, the negative charge is on the oxygen. So what do you think? Which one is more stable? So we know that oxygen is more electronegative than carbon, so it likes to take the negative charge, meaning that this anion is more stable than this one. Therefore, the alcohol is the stronger acid than the alkane. And we can even compare the pKa values here. So the pKa for an alcohol is 16, and for alkane is 50. So even the pKa confirms our work. So now here is the rule here. Carbon and oxygen are in the same row. So when we are comparing the atoms on the same row, the more electronegative atom will better stabilize the negative charge always. So when you are comparing atoms in the row, you need to consider the electronegativity concept. In another example, so imagine that I have water, and I want to compare that with hydrogen sulfide. So I want to know which one is stronger acid. So the first step is to draw their conjugate base. The conjugate base for water, this hydroxide anion, and here is the conjugate base. hydrogen sulfide. To compare these two anions, we have negative charge on oxygen here, and in this structure we have it on sulfur. So if you look at the periodic table, oxygen and sulfur are in the same column. So when atoms are in the same column, the size is an important factor for stabilizing the conjugate base. So as we go down the periodic table, so going down, the size increases, meaning that the negative charge is more stable on sulfur rather than on oxygen. So this anion is more stable than this one. So hydrogen sulfide is a stronger acid than water. And we can even compare their pKa values. So the pKa value for hydrogen sulfide is 7. And for water is 15.7. So when you have atoms in the same column, you need to consider their size. The larger the atom, the more stable the negative charge will be. The other factor is resonance. We talked about resonance and how to draw resonance structures before. It's also a stabilizing factor here. So if you compare these two molecules, ethanol versus acetic acid, so we want to know which one is more acidic. The very first step is to draw their conjugate bases. Removing proton. This is the conjugate base here. And for this one, the conjugate base is this molecule. So in this example, the atom that bear a negative charge is oxygen in both molecules. So we cannot compare atom. However, if you remember the resonance pattern, in this anion, the lone pair is allelic to the double bond. So it can do resonance. We can draw a resonance structure for that. Hopefully by now, you feel comfortable drawing resonance structures. This is the resonance structure for this anion. And we'll put them in brackets. However, this anion, it cannot do resonance. So we call this anion, we say that this anion is resonance stabilized and the charge is delocalized. The negative charge is delocalized in this anion. However, the negative charge in ethoxide is localized. Therefore, the negative charge is more stable on this anion, meaning that the acetic acid is more acidic than ethanol. So if we can compare the pKa values even, the pKa value is 4.75 here, and for alcohol is 16. Now in this bottom example, we want to know which hydrogen is more acidic, the blue one or the red one. So to identify that, we first need to draw the conjugate bases for each side. I start with the left. So the conjugate base, I remove the proton. Don't forget to draw the lone pairs and the charge. And for the left side, okay. These are the conjugate bases for each side of the molecule. Now we need to compare and see which conjugate base is more stable. So if you look at this anion, the negative charge is on a nitrogen, and on the right side the negative charge is also on a nitrogen. So comparison by atom is not a good idea here. Now this anion has a double bond allylic to it has a lone pair allylic to double bond, so it can do resonance. Let's draw the resonance structure for that. Pushing the lone pair here. Alright, so now as you can see, this anion can do resonance, but this one cannot. So this anion is more stable than the other one, meaning that this proton is more acidic. We can even compare the pKa. So this functional group here is an amine, and R2H is an amine, and the pKa for amine is 38. And this part of the molecule, if you remember the functional group, this functional group is amide. The pKa for amide is 15. So amide is more acidic than amine. Alright, the next factor is induction. Induction stabilizes a formal negative charge by withdrawing electron density. So what does that mean? Let's look at this example. We have acetic acid versus this acid. Forget the lone pairs. Now we want to know which molecule is more acidic. So the first step is to draw their conjugate bases. This is the conjugate base for this molecule. And this one is a conjugate base for this molecule. Okay, so in both of these anions, both conjugate bases, we have the negative charge on oxygen. So atom is not a good factor. Both of them are carboxylic acid, so they both can do resonance. Therefore, resonance is also not a good factor. The only difference between these two molecules is that we have 3 chlorines attached to this carbon right here. However, we have 3 hydrogens attached to this carbon. We know that chlorine is more electronegative than hydrogen. So these chlorines will pull the electron density from the central carbon atom and toward themselves, so they can stabilize the negative charge. Basically, what I can say is that this anion has more hands to hold this negative charge. Therefore, this negative charge is more stable on this anion comparing to the other one. Therefore, this molecule is more acidic than acetic acid. We can even compare their pKa values. So the pKa value for this molecule is 0.7, and the pKa value for acetic acid is 4.75. There are a few rules with induction effect. So when you add more electron withdrawing group to the compound, the acidity of the compound will increase. So for example here, the acetic acid, the pKa for that is 4.75. When you add 1 chlorine to the molecule, the pKa decreases. When you add 2 chlorines to the molecule, the pKa is going to be 125, even it decreases more. And with 3 chlorines, the pKa would be 0.7. So as you add more electronegative atom to the molecule, the conjugate base would be more stable. Another factor is that the more electronegative that group is, the more stable the conjugate base would be. So what does that mean? If you look at these two molecules, and compare them together. So in this one, we have fluorine attached to the molecule, and in the other one we have bromine attached to it. So in the periodic table, we know that fluorine is the most electronegative atom in the periodic table. Therefore, the more electronegative this group, the more stable the conjugate base would be. So if we compare the acidity, that molecule is more acidic than the other one. Another important factor is that the closer the electron withdrawing group to the basically negative charge center, the more stable the conjugate base would be. So if we compare these two molecules, I have chlorine here, so in this molecule, if you draw the conjugate base for both of them, this is the conjugate base here, and then this one, this is our conjugate base. So as you can see in this molecule, chlorine is closer to that negative charge comparing to this chlorine, meaning that this conjugate base is more stable than the other one. So this molecule is more acidic than the other one. So this is more acidic. The last factor is orbital. The orbital that is holding the pair of electrons in conjugate base is very important in stabilizing the negative charge. So generally, when electrons are closer to nucleus, they are more stable. Now, if you compare the shape of sp3, sp2, and sp orbital, you notice that sp3 orbital is longer because it has more p character. There is 3 p orbitals and 1 s orbital there. So if I do a little bit of math, sp3 orbital has about 25% s character and 75% p character. Now if you look at sp2 orbital, we have more s character there, 33%. And for sp orbital, we have 50-50% for both s and p orbital. So basically, when electrons are in a longer orbital, they are far away from the nucleus, so they are less stable. Now let's take a look at the example below. We want to know which hydrogen is more acidic. So the very first step is to draw their conjugate base for each side. So for this side of the molecule, conjugate base is this one. And for the other side of the molecule, we have this conjugate base. Now we want to know which conjugate base is basically more stable. So this charge, as you can see, reside in sp2 orbital. So here we have an alkene, so this is sp2 orbital, and this side, the negative charge, is in sp orbital. So when the electrons are in sp orbital, basically the sp orbital is shorter, so electrons are closer to nucleus, therefore they are more stable, meaning that this anion is more stable than this one. So this proton is more acidic than this one. So this is more acidic. So to draw write our conclusion, the order of acidity sp is more acidic than sp2 than sp3. So we can, for example, for sp, we can have a compound like this. This is sp2, and we have alkane for sp3. We can even compare their pKa. The pKa for sp is 25. For alkene, it's 44, and alkane is 50. So sp orbital is more acidic than sp2 and than sp3.